This is section 3.2, and we start with our definition of subspaces and some examples. So, subspaces. Now, they are mostly, they're just looking at our usual vectors. That kind of thing. But I'll toss in a couple of examples that aren't exact, that don't look like they're as related to the stuff we've been doing, equations and matrices and that kind of thing. So they call it definition 3.21. And so we're talking about a subset. So a subset of Fn. Let me try that again. Okay, so a subset S of Fn. So again, the F part is just any sort of field. And so, it could be integers, mod, something, usually it's just our real numbers. So usually this is just Rn, but it could be something else. And so it's a subset of whatever we're working with is called a subspace. So see, I can have lots of things that are subsets, but not as many things that are subspaces. So it's a subspace of Fn if, and we have three criteria. One, the zero vector is an element of S. Okay, so is an element of, is that little epsilon there, lowercase. And so that has to be in there. Then two, if U and V are both in S, then their sum is, then U plus V is an element of S. And then finally, if U is an element of S, okay, and T an element of F. Now again, for us, this is almost always just the real numbers here. They're saying some field, but it's just the real numbers for us most of the time. Then T times U is an element of S. So we have addition and scalar multiplication. It has to be closed. Okay, so closed under this plus. Okay, and closed under, and I don't have a symbol for scalar multiplication, so I'll just say scalar multiplication. Okay, so that's our definition. Now, what are some examples? Well, our examples, they go through and some very important ones. We're going to look at null space, column space, row space, of a matrix A. Okay, so we start with the null space. Oops, I forgot space up there after column, but so null space, and we actually, well, let's see, of A. Okay, and we denote it just with an n of A like that. That's our null space. And null space of A is X is an element of the null space of A if A times X gives you the 0 vector. Okay, so pretty straightforward. Well, one, so is this really a subspace? Well, one, we check if 0 is in there. A times 0, well, we know that's 0. So 0 is indeed an element of, well, let's see, I'm using n of A there, so let me get that right, n of A. So that's great. Now, how about addition? Well, so what we have to say is something like, X and Y are elements of n of A. And so now what we have to do is look at, something like let Z equal a vector X plus the vector Y, or I could have used X1, X2 kind of thing. Well, so now we need to see if A times Z is equal to 0. Well, A times Z is equal to A times X plus Y. And then I can use the distributive property. I have AX plus AY. But now those are both in our subspace, so I know that's a 0 vector and plus a 0 vector. And I get a 0 vector. Okay, great. So this works. And then finally 3, if I, let, well, if we say, X is an element of the null space of A, and T is an element of the real numbers, and we let, say, Y equal TX. Now we need to look at AY. So AY, that's equal to A, and I just use my definition of what I defined Y to be, and that's the TX. But now I have that I can pull the T out under scalar multiplication, and so that's T times AX, but AX is 0, so that's T times the 0 vector, and then that's the 0 vector. Okay, great. So we showed that this is indeed a subspace, so N of A is a subspace of all right, over here are N. Okay, so now the N, I never mentioned it up here, I guess, but A would be is M by N. Okay, so null space, that's one down, and then let's see, I guess, yeah, I'll mention there. So notice, notice if A is non-singular, then N of A is only the 0 vector. All right, if A is non-singular, and then the null space is only the zero vector, because if we have this and A is non-singular, I can multiply both sides by the inverse. A inverse 0. And on this side I get the identity times x. This side I get the zero vector, and then I get x is the zero vector only. Right? So if A is non-singular, the null space is pretty small. But on the other hand, you know, if we do something like, you know, let A equal 1, 2, 2, 4, then notice I can do a pretty quick row reduction here. If I can zero out the second row by taking -2 times the first row plus the second row, putting it in there, and so my reduced row echelon form takes me to 1, 2, and if I had augmented with the zero vector, 0, 0 like this, and so what I get is that from this, x is equal to -2y, and so I guess I could write that then as the vector. Now, let's see, I need to make that taller. Whoops. So I end up with this vector, what is it, -2, 1, right? If y is 1, then x would be -2. But then, again, the null space is closed under scalar multiplication, so I can multiply that by t, and of course if t equals 0, then I get the zero vector. But this, the set of x such that x equals t times this vector -2, 1, that is my set S, or, well, actually better yet, right, N of A. Okay, that's everything that satisfies that subset. So, you know, I've got my null space of A that way. Whew. Okay, let's see. Let's keep going. So now, the column space, okay, column space of A, okay, I'm looking to see, do they give a notation for that? Yeah, they do call it C of A. So this is C of A. The column space of A is all linear combinations of the columns of A. Okay, now we want to see that that is a subspace, but so what we're looking at here is, you know, if I said A is equal to the matrix, and I call it, I'm going to call it A.1, A.2, A.3, comma, like that. Put little lines over these because these are column vectors, you know, all the way to some A dot n. Now I'm using the A dot n because that kind of goes with our Sage Math and Python, that you might use a dot and then a second indice for the column. But so if we have that, then what we're talking about is that S is equal to X such that, okay, so I use the two dots for such that, well, actually, again, let me try using a Y here. Just will look better for us. A sub Y such that I could get Y by taking A times some X equals Y. Right? In other words, I can find some solution, any Y's for which I could find a solution to this. And what that is they point out, you know, I'm taking when I do that, that's my linear combinations of the columns, because you see I get that, you know, AX is X1 times A dot 1 plus X2 times A dot 2, you know, plus all the way to Xn A dot n. Okay, so something like that's linear combinations of the columns, but that's what happens when I multiply on the right by a vector. You know, when I take A times X like that. And so now, you know, let's check this out. You know, are there solutions? So one, how about the zero vector? Is the zero vector in S? You know, and I'm saying it is, since A times 0 is equal to 0. Okay, now this linear combination, see if I take 0 times the first column plus 0 times the second. So a linear combination can be all 0 multipliers, and so that's what I did, was I let all the x's be 0, and I get 0. So 0's in there. Okay, 2. Well, okay, so let's do this with a y1 and a y2. So suppose I have a y1 and a y2. They're elements of S. And so now I'll let I guess y equal y1 plus y2. Okay, so now I need to know, does, well, that's kind of an interesting way to spell it. Does AX equal Y have a solution? Okay, that's what I need to show in order to show that Y is in here. So see, it's a little odd trying to, you know, show this, but sure, I can show it. So I need to produce that solution. Well, so if I let X equal X1 plus X2, where AX1 equals Y1, and I know that exists because Y1 was in S, and AX2 equals Y2, and I know that's there because Y2 was in S. Then I can show that AX is equal to A times x1 plus x2, which is equal to AX1 plus AX2, but that is Y1 plus Y2, which is Y. And so you see I can get Y from that linear combination there of, using that vector X, linear combination of the columns, I can get Y. And so, great, that was number 2. And finally, number 3, again, what I do is I have, how did I state this before? Okay, I just went with, okay, so let's say Y1 is an element of S, okay, and T an element of Rn, okay. So if Y1 is an element of S and T is some element of Rn, I'm going to need to look at Y equal T times Y1. And I want to see, is that in S? Can I show that that's in S? And again, I do that same thing. I will say let x1 be such that AX1 equals, try that again, AX1 equals Y1. Okay, so, and I know I can find that x1 because y1 is in S. And so now let x equal tx1. And so now I'll show that ax does produce y. So ax is equal to a times tx1. But that's just tax1, which is t times y1, which is the y we needed. And so there we have all three. We've got it's closed under scalar multiplication, closed under addition, and it does contain the zero vector. And so C of A is a subspace. Column space, I would just work with, column space, row space. So row space is like column space, but it's all linear combinations of the rows of A. Row space use A transpose and repeat steps of column space. Okay, so we can do that, and now one more thing. I guess this has gone on long enough, so I'll do more examples in another video. But we do talk about spanning a space. And so what we would say here is that the columns of A span C of A. Okay, and a spanning set and I'll do well, I'll use A's. A1, A2, up to some an. Okay, a spanning set of a subspace, I have trouble with that B, I guess, of a subspace, S, is a set such that all linear combinations of those, so such that any y element of S can be written as y equal x1 times a1 plus x2 times a2 plus all the way out to xn times an. Okay, so it's a linear combination. If I can take any vector in S and write it as a linear combination of this set of vectors a1 to an, then we call that set a spanning set, or it spans the a space. Okay, so just by definition, the columns of A span the column space of A. Okay, just by definition, because it can't be in here unless it's a linear combination of the columns. Okay, so like I say, that's enough of that. That was a long one. So we'll do examples in a